So in the previous video, I explained how I compressed relative distances to the resources by just including relative distance of x and z to the target. And in that video, I showed you this function where how these states gets computed and briefly mentioned that the way this gets computed has changed due to these extra code. And in today's video, I'd like to explain the differences. So the function used to look like this where, this one, it used to look like this where it works pretty simple that I just compute the target vector by just subtracting position vector of AI from position vector of whatever nearest target the AI agent is aiming for at the step. So on every step, the AI has to follow or chase the target. That depends on the condition of the states. For instance, if he's hydrated, he needs to go for water, but he can't just go for whatever water he's around. Whatever water he can get, but he just go for closest or nearest water from his position. And so this could be if the target is water, this will be the position vector of closest water. So and subtracted by position vector of AI, I get target vector or relative distance, which would look like this so this is the target vector, and where agent at 2, 3 and target at 5, 7, and 3, 4 is the target vector or relative distance. And so why did I have to improve or add extra code? So it works, this works fine if my AI agent never changed his direction. But as you can see, he changed his direction or he rotates, and it wouldn't really go if he changes his direction. And the reason is, so let's say, so I have value for his direction using radians. It starts from on each episode. Whenever each episode starts, his direction is 0 degree or 0 radians. And if I assign that to this sine cosine function, it would be forward vector. I'll get forward vector of 0, 1, which would look like this. And this function would work if he never rotates or his direction is always 0 radians, because in this case he just has to learn that he has to go to the right. He has to go 3 units to the right and 4 units to the front, and maybe the target and his position might be different, but as long as his direction never changes, it will be like this, where it's quite relative to him, the relative distances. It's always, the dx is always the amount of units he has to move to the right, and same goes for dz. So it's fine, but like I said, he rotates. So imagine if he has rotated 90 degrees or pi over 2 radians, making him facing towards this way. And what happens is that this function no longer really works well. And the reason is, so previously, if his direction was in this way, was zero degree, you just have to learn that the target is 3 units to the right, 4 units to the front. But that doesn't really apply if he's facing pi over 2 radians to the right, because as you can see, if he used the same method he has done when his direction was 0 degrees, so 3 units to the right would be here, and 4 units to the front would be this. And this is clearly a wrong target, because actual target position, the actual target position vector is here. I mean, the actual position is here, but I just created fake target vector when I use the same method for aiming for the target when the direction was 0 degree. So this is just this is just inconsistent. Like these are just data set for a neural network, and he doesn't even know, the AI doesn't know whether this is to the right, that this is the amount of units to the right or amount of units to the front. He doesn't know. So the only way he can learn consistently is to me providing him a consistent data set. And to do that, it would be better if it would be better if his direction never changes, meaning direction is always 0 degrees or 0 radians, so that relative distances would be always relative to the AI. So the reason these are problematic is for this direction, for the case the AI is facing this way, both from world and agent coordinate systems perspective, it's 3,4. From AI's perspective, it's 3 units to the right, 4 units to the front. And this is 3,4 in the world coordinate system, so it's correct. But once I change the direction of AI, the world coordinate system, it's still 3,4, but in agent coordinate system, this is not 3,4. If he's facing this way, it's actually 3-4 from here. 3 units to the front and -4 to the left. Like as if he was in the origin, this would be the correct value for that. And I computed this just by using the newly added code, which just takes dot products. So essentially what I'm doing with these code is converting value, those value what I'm essentially doing is converting these values from world coordinate system to agent coordinate system, so that these would be always relative to AI or agent frame, so that I would avoid the inconsistency. So, and it would essentially means I rotate amount of I would, by doing this, by taking dot products, I'm essentially rotating this false target vector by amount of angle he has rotated. I'm using DirectX, so normally when you rotate, so when AI was facing this way, and when you rotate this way, it would be negative 90 degrees, but I'm using DirectX 11 by default. It's opposite, so if I rotate in this way, it would be positive 90 degrees of pi over 2 radians. So to reverse that, I have to rotate back by negative 90 degrees. So if I rotate this by negative 90 degrees, it would essentially be target vector, like I would turn this false target vector to this correct target vector. And so this would be as if he's at the origin facing 0, 1, or the direction is 0 degree or 0 radian. So the way let me just compute forward, and so I just compute the forward and right vectors, and these equations are for when the direction is 0 degree. So sine of 0 is 0, and dx is 3 plus cosine of 0 is 1, and times dz is 4. So I'll get 4 for forward vector, and I do the same thing for the right vector, and I'll get 3. So these are essentially same as when I did computation for this is exactly how the values I'll get when I use this. So it's pretty similar, but this forward vector tells you how much to the front or to the behind the target is from AI's perspective. So if this is positive, it means the target is in the front. If not, it's to the back, to the behind. And the same goes for the right vector. If it's positive, it's to the right, and if not, it's to the left. So in this case, from if the direction is 0 degree to the 4 units to the front and 3 units to the right, so exactly the same as this. But it would get convenient if I use this in this situation, and if I do the calculation, I'll get 3 for 3 and negative 4 for forward and right vector respectively. And what this means is if he's facing this way, the target is 3 units to the front and negative 4 to the left. And this is exactly where the target is. And this 3 and negative 4 means it essentially encodes better than this 3, 4, because now these values are relative to AI, or this is in AI's coordinate system rather than just pure world coordinate system. So if I just feed my AI the values for relative distances, in agent coordinate system consistently, he would know. I mean, it would be easier for AI to learn, because again, it's the values relative to the AI. So yeah, and that's just what I did. for the newer version, I just introduced the new coordinate system, the AI agent coordinate system. And after I've started using this, I think his behavior and performance has improved, I guess. And I think there are more way more different methods to improve his, I don't know, like the way he moves and locomotions. But as far as I know, this is the best knowledge I can apply for that to improve my AI. So yeah, this is it, and this is what I wanted to explain. So yeah, thanks.